Welcome to The Explainer. Today, we're looking at a new paper that could literally change how innovation works. We're talking about an AI that doesn't just learn what we teach it, it actually discovers brand new and better AI models all on its own. Think about that for a second. Imagine a system where the speed of discovery isn't limited by a person having a brilliant idea in the shower. Instead, it's only limited by how much computing power you can throw it in. The more GPUs you add, the faster it invents. That is the wild idea here, trying to automate scientific discovery itself. But to really get why this is such a potential game changer, we first need to talk about the huge problem in AI development that this is trying to solve. So here's the paradox of AI right now. On one hand, our computing power is just exploding. We have these massive data centers with hundreds of thousands of GPUs, and that power is growing exponentially. But on the other hand, the rate of new, groundbreaking ideas, well, that's still stuck at human speed. It's limited by our creativity and our time. We are the bottleneck. So, to try and smash through that human bottleneck, researchers have built a system specifically designed to automate the messy, creative process of scientific innovation. They're calling it ASI ARC. Now, you might be sitting there thinking, hang on, haven't we used AI to design AI before? And yeah, you're right, we have. But the old ways, like something called neural architecture search, or NAS, were kind of like explorers with a pre-drawn map. They could only mix and match building blocks that humans had already given them. ASI ARC is different. It's not just an explorer, it's designed to be a true inventor. It comes up with totally new concepts from scratch. Okay, so how on earth does it work? Well, the whole system is this closed, self-improving loop. The best way to think about it is like a tiny automated research team with 4 key players all working together perfectly. So those 4 roles are the researcher, the engineer, the fitness score, which is basically the judge, and the analyst. And together they create this incredible cycle of coming up with ideas, testing them, judging them, and then learning from the results. First up, you've got the researcher. This is the creative brain of the whole operation. It literally reads scientific papers and looks at all its past experiments to dream up completely new ideas. And it doesn't just spit out a concept, it actually writes the code for the new AI it just invented. That new code then gets handed off to the engineer. Its job is to take that fresh idea and actually train it, put it through its paces. And here's the really mind-blowing part. It has a self-revision feature. So if the code has a bug, the system doesn't just crash and throw the idea away. It actually looks at the error and tries to fix its own code. That is a massive leap forward. But how does it know if an idea is actually good or just weird? That's where the fitness score comes in. And this is super clever. It's not just about getting the highest score on a test. It blends the hard numbers with a qualitative review from another large language model that acts as an expert judge. This judge looks for things like elegant design and actual novelty. It stops the system from just gaming the numbers. And finally, there's the analyst. This part is the system's memory. It takes everything that happened, the scores, the bugs, the successes, the failures, and pulls it all together. It updates the system's central knowledge base, making sure that every single experiment, good or bad, makes the whole loop smarter for the next go-around. Okay, I know what you're thinking. Testing thousands of new AI models sounds insanely expensive. And it would be. But they came up with a really smart 2-stage strategy to handle it. First, there's an exploration phase that runs quick and dirty and cheap. Tests on small-scale models just to see what's promising. Then, only the absolute best ideas get promoted to the verification stage for the full, expensive, rigorous testing. It's a brilliant way to find needles in a haystack without burning a mountain of cash. So, after all of that, the loop, the smart strategy, nearly 1,800 experiments running for 20,000 GPU hours, did it, work? What did the AI actually find? The result is pretty stunning. 106. That's the number of totally new, state-of-the-art AI architectures that this system discovered all by itself. The researchers who built it are calling this a new AlphaGo moment. And just as a quick refresher, the original AlphaGo moment back in 2016 was when DeepMind's AI made a move in the game of Go, Move 37, that was so creative and so alien that it just floored the world's best player. It proved that AI could come up with strategies that were beyond human imagination.
The way it got there was basically through evolution. It started with just one parent model, designed by a human. Then it started creating children by tweaking that parent's code. Some were worse, those are red or yellow. But some were superior, the dark blue ones. And what you see is that over generations, it started producing more and more dark blue models, learning from its own successes.
And when you put them head to head, the proof is in the pudding. The AI's creations consistently beat the best human designs in this specific area. They got higher performance scores and they made fewer errors. I mean, simply put, they were just better. But here's the part that really gets me. Look at where the best models actually came from. Yeah, it started with a human idea. But a whopping 90% of the top-performing models were generated from the AI's own discoveries. It wasn't just remixing our work. It was genuinely building on its own creative leaps. So these results are obviously exciting, but they also bring up a much, much bigger question. What does this mean for the future? If this really works, it could change the entire engine of science. And this brings us right back to that bottleneck we started with. If you have a system like this, maybe the pace of discovery isn't tied to the slow, steady pace of human researchers anymore. Maybe it becomes directly tied to something we can scale exponentially. Compute power? GPU hours? In theory, more compute could literally mean more scientific breakthroughs. Now, of course, let's keep things in perspective. This is not the Holy Grail, yet. The study had some important limitations. It was focused on a pretty specific, narrow type of AI model, so we don't know for sure if this same method can be used to design the giant, complex models like a GPT-4. It's an absolutely groundbreaking first step, but it's still very much the first step on a long road. And that leaves us with one final, absolutely fascinating thought to chew on. If we can build an AI that can design a better AI, what else can we point it at? What other monumental problems in medicine or material science or climate change could a system like this help us solve? That's the real question. Thanks for watching.